You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your Security Plus certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Connectivity refers to the set of links, devices, and protocols that allow systems to exchange information. It includes physical links such as Ethernet cables or fiber optics, wireless connections like Wi-Fi and cellular, and logical protocols such as TCP/IP that govern how data is formatted and delivered. Reliable connectivity is the backbone of every IT system, enabling users to access resources, applications to communicate, and data to flow securely. Weaknesses in connectivity design can lead to downtime, degraded performance, or even total service loss. By treating connectivity as an architectural element, organizations ensure communication pathways remain resilient, efficient, and aligned with operational goals. Network topologies influence both availability and resilience. A star topology centralizes connections through a hub or switch, simplifying management but creating a central point of risk. Mesh topologies interconnect nodes directly, providing multiple paths and high resilience at the cost of complexity and overhead. Hub-and-spoke models, common in large organizations, route branch offices through central data centers, simplifying routing but increasing dependence on the hub. Each topology carries trade-offs in cost, complexity, and failure tolerance. Understanding these patterns allows architects to align topology with business needs, whether emphasizing simplicity, cost efficiency, or maximum resilience against outages. Single points of failure, SPOFs, are components whose failure results in systemic outages. A lone router, an unreplicated database, or a single cloud availability zone all represent SPOFs if no redundancy exists. SPOFs are dangerous because they negate resilience by concentrating risk. Attackers and natural failures alike exploit these weaknesses, causing disproportionate impact. Identifying SPOFs requires mapping dependencies and understanding how failures propagate through systems. Eliminating them often involves redundancy deploying backups, alternative links, or clustered systems. Effective architectures prioritize SPOF reduction, recognizing that continuity depends on ensuring no single device or service has the power to collapse operations entirely. Failure modes describe the various ways systems can break. Hardware failures occur when physical devices such as switches, disks, or CPUs fail. Software failures include bugs, memory leaks, or unpatched vulnerabilities causing crashes. Configuration errors often create failures by misapplying settings, opening insecure routes, or disabling critical features. Human error, such as miskeyed commands or flawed updates, remains one of the most common sources of outages. Each failure mode requires different mitigations: spares for hardware, patching and QA for software, automation for configuration, and training or guardrails for humans. Recognizing these categories helps organizations plan proactively, ensuring no single type of failure is ignored. Link-level failures are among the most fundamental connectivity issues. They occur when a cable is cut, a fiber loses light, or an interface shuts down. Detection is usually straightforward, with signals such as loss of carrier or interface down logged by devices. However, detection must also be rapid and actionable. Redundant paths and link aggregation help ensure service continuity, but only if systems detect and switch over effectively. Monitoring tools must capture both physical link failures and transient issues like flapping. Proper architecture recognizes that physical links are fragile, and designs must anticipate their inevitable failure and recovery needs. Routing failures reflect problems with how traffic paths are determined. Misconfigurations may create black holes where traffic disappears, or loops where packets circulate endlessly. Route flapping, where routes oscillate between states, destabilizes connectivity, creating intermittent outages. Incorrect path selection can also lead to inefficient or insecure routing, sending data through suboptimal or risky networks. Detecting routing failures requires visibility into routing tables and dynamic protocols. Preventing them involves careful configuration management, redundancy in routing protocols, and monitoring for anomalies. Architecture must assume that routing errors will occur and build safeguards that minimize disruption when the control plane malfunctions. Congestion-related failures occur when network demand exceeds capacity, leading to latency, jitter, and packet loss. For latency-sensitive services like video conferencing or VoIP, even minor congestion can degrade quality. For transactional systems, congestion creates timeouts and failed operations. Congestion is not always constant. It often spikes unpredictably, such as during distributed denial of service, DDoS attacks, or peak business hours. Mitigations include capacity planning, quality of service, QoS prioritization, and scalable bandwidth strategies. Without addressing congestion, availability becomes unpredictable as overloaded links throttle performance. Robust architecture treats congestion not as a rare anomaly, but as an expected condition requiring constant management. Redundancy mitigates connectivity failures by ensuring alternative paths exist when one fails. Redundancy may involve multiple physical links, dual routers, or geographically diverse data centers. The effectiveness of redundancy depends on independence. Two redundant cables in the same conduit are not truly redundant. Redundancy also requires orchestration so that failover happens automatically without disrupting users. This principle is not about eliminating failure, but ensuring it does not lead to systemic collapse. Resilient connectivity designs always assume links or devices will fail and provide alternatives that maintain continuity seamlessly, reducing downtime to seconds or even milliseconds. Failover mechanisms govern how systems switch from primary to backup resources during outages. Active/passive failover designates one system as primary and another as standby, activating the latter only during failure. Active/active failover keeps multiple systems running simultaneously, balancing load while providing redundancy. Protocol-based failover, such as HSRP or VRRP for routers, provides automatic switchover at the network layer. Each approach carries trade-offs. Active/passive is simpler, but may involve brief downtime, while active/active is seamless but more complex. Selecting the right failover mechanism ensures recovery strategies align with service criticality, balancing cost with continuity. Monitoring and alerting are essential for early detection of connectivity degradation. Metrics like latency, packet loss, and error rates must be tracked continuously. Threshold-based alerts notify operators before complete failures occur, enabling proactive remediation. For example, rising error counters on a switch port may signal an impending hardware failure. Without monitoring, failures manifest only as user complaints. With robust monitoring, organizations detect and correct issues early. Monitoring systems must also validate failover operations, ensuring redundancy actually functions as intended. Embedding proactive visibility into architecture ensures that connectivity problems never remain invisible or unresolved for long. Documented recovery procedures provide clear guidance for restoring connectivity when failures occur. These procedures should outline step-by-step actions for hardware replacement, configuration restoration, routing revalidation, or traffic rerouting. Documentation also includes escalation paths so teams know who is responsible at each stage. Without documentation, recovery becomes chaotic, dependent on memory or improvisation. Documented procedures reduce human error during crises, ensure consistency across incidents, and improve confidence in recovery times. Architecture must assume failures will happen and embed recovery procedures into governance, ensuring resilience depends on practice discipline, not ad hoc heroics. Proactive testing validates resilience by simulating failures before they occur naturally. Techniques like chaos engineering or deliberate link shutdowns test whether failover, redundancy, and monitoring behave as expected. Proactive testing exposes weaknesses, such as misconfigured failover paths or ineffective alarms, before adversaries or real failures exploit them. It also builds operator confidence, showing that architecture can withstand disruption without significant downtime. Testing should cover link failures, routing anomalies, and even full-site outages. By treating resilience as something to prove, not assume, proactive testing transforms architectural resilience into demonstrable reality. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Load balancers play a central role in handling endpoint failures and distributing traffic efficiently. They monitor back-end servers and redirect requests to healthy instances when one fails. This prevents users from experiencing downtime even if individual systems are offline. Beyond resilience, load balancers also optimize performance by spreading requests evenly across nodes, preventing bottlenecks. They can be deployed at both local and global levels, managing traffic within a data center or across multiple regions. By combining availability with efficiency, load balancers transform connectivity into a dynamic process. Their presence ensures systems remain accessible, even under failure or heavy demand conditions. Link aggregation and multipath strategies provide redundancy and bandwidth improvements simultaneously. Link aggregation bundles multiple physical connections into one logical link, increasing throughput while offering resilience. If one link fails, traffic continues over the remaining ones. Multipath routing, meanwhile, uses multiple independent routes for traffic, balancing load and ensuring continuity. These approaches protect against both hardware failures and congestion by distributing traffic dynamically. However, they require careful configuration to avoid loops or misrouting. When deployed effectively, link aggregation and multipath strategies minimize single points of failure at the link layer, strengthening overall connectivity and bandwidth capacity in resilient architectures. Health checks are critical for enabling automated failover decisions. These checks continuously probe endpoints to confirm availability, such as verifying HTTP responses, pinging devices, or querying service health APIs. If an endpoint fails a health check, orchestration systems or load balancers remove it from service pools automatically. Health checks must be designed to reflect true functionality, not just superficial availability. For example, ensuring a web server returns correct page content, not just a TCP handshake. Poorly designed checks may produce false positives or negatives, undermining reliability. Robust health checks transform failover into a precise, automated process, ensuring traffic always flows to functional resources. Degraded mode operation allows systems to continue functioning at reduced capacity during failures. Instead of collapsing completely, services adapt by offering limited functionality until recovery occurs. For example, a payment system might restrict certain non-essential features but still allow basic transaction processing. Graceful degradation ensures continuity for core functions, even under partial outages. This strategy enhances resilience by avoiding abrupt disruption for users. It also provides organizations with breathing room to remediate failures without full downtime. Designing for degraded modes requires identifying which features are essential versus optional, embedding resilience into the application and infrastructure from the ground up. DNS failures can have a disproportionate impact on connectivity because they prevent users from locating services, even when infrastructure remains healthy. Outages in DNS resolvers or misconfigured records can render entire domains inaccessible. Mitigation strategies include deploying multiple redundant resolvers, using short time-to-live (TTL) values to propagate updates quickly, and employing global DNS providers with distributed infrastructure. Split-brain scenarios must also be avoided by ensuring consistency across records. By recognizing DNS as a critical dependency, organizations plan redundancy and monitoring specifically for it. Without such planning, DNS failures can undermine otherwise resilient connectivity, highlighting the need for systemic awareness. Latency-sensitive services require special consideration for connectivity resilience. Applications such as video conferencing, VO, and online gaming cannot tolerate delays or jitter beyond narrow thresholds. Even if connectivity exists, performance degradation renders these services unusable. Architectures must account for geographic distribution, quality of service, QoS prioritization, and redundancy specifically designed to minimize latency. For example, routing through closer data centers or reserving bandwidth for voice traffic ensures continuity. Latency-sensitive systems remind us that resilience is not only about uptime but about quality. Without specialized design, high availability fails to deliver meaningful usability for these workloads. Automated remediation provides speed and consistency during failures, but it carries trade-offs compared to manual intervention. Automation can restart services, reroute traffic, or spin up new resources immediately, minimizing downtime. However, poorly designed automation may act on false signals, worsening problems or creating instability. Manual intervention allows for careful diagnosis but takes longer, extending outages. Effective architectures strike a balance by automating predictable, low-risk responses while reserving human decision-making for complex failures. This hybrid approach ensures resilience is preserved without unnecessary risk, embedding both speed and discernment into operational practice. Capacity planning is essential to avoid failures due to oversubscription. Networks, servers, and links must be designed to handle peak loads, not just average demand. Failing to account for surges leads to congestion, dropped packets, and degraded services. Attackers also exploit poor capacity planning through denial-of-service attacks, overwhelming under-provisioned systems. Proper planning involves modeling traffic, monitoring growth, and provisioning additional resources proactively. Scalable designs, such as elastic cloud infrastructure, adapt dynamically to load. Without planning, resilience falters under predictable stress. With it, connectivity remains reliable, ensuring performance remains steady even when demand spikes beyond expectations. Logging of failure events provides the data needed for root cause analysis. Every failure, whether hardware, software, or configuration, must leave a trail that can be reviewed to understand why it occurred and how to prevent recurrence. Logs should capture both technical details, interface down, routing flap, and contextual factors, time of failure, load at the time. Centralized logging simplifies analysis across environments, while retention ensures historical failures can be studied. Without logs, failures remain anecdotal and reactive fixes repeat. With strong logging, organizations transform failures into learning opportunities, building more resilient connectivity over time. Rollback strategies ensure that changes causing connectivity failures can be reversed safely. Misconfigurations in routing tables or firewall rules are common causes of outages. Rollback procedures allow administrators to revert quickly to a known good state, minimizing downtime. Safety mechanisms, such as automated reversion if connectivity drops, add further assurance. Rollback planning must be built into architecture and operational workflows, not improvised during crises. Without it, small mistakes escalate into prolonged disruptions. Rollback provides confidence to make necessary changes, knowing that recovery is quick and reliable if unexpected consequences arise. Change control windows reduce the risk of failures during updates by scheduling modifications during low-demand periods. These windows ensure that technical staff are available to monitor outcomes and intervene if needed. Combined with staged rollouts and validation, change control minimizes the chance of widespread outages from configuration changes. While some may view this as slowing agility, it is a proven safeguard against preventable failures. Architecture must balance agility with discipline, ensuring changes align with both operational needs and resilience requirements. Change control transforms updates from risky events into predictable, manageable processes that protect connectivity and service continuity. Ultimately, design and operational practices together reduce downtime from connectivity-related failures. Architecture defines redundancies, failover paths, and degraded mode operations, while operations provide monitoring, capacity planning, and disciplined change control. Both layers reinforce each other, ensuring failures are anticipated, detected, and remediated effectively. Connectivity resilience is not achieved by any single control but by a combination of redundancy, observability, and governance. By embedding these practices into design and daily operations, organizations minimize the impact of inevitable failures. Resilient connectivity is not just about surviving outages, it is about sustaining trust, performance, and business continuity under all conditions. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.